has y-axis symmetry, it can fold over the y-axis and land on itself. It has x-axis symmetry, it can fold over the x-axis and land on itself. Does anyone know what origin symmetry is? Good. It can rotate around the origin and land on itself, or if you reflect it over the x and y-axis, both it would land on itself. So either one of those thought processes will work. You did learn this in geometry. So, which one has, what does the first graph have? X-axis symmetry, because it folds over the x-axis. Does everyone agree? What about the bottom middle one? Y-axis. And what about the last one? Origin symmetry. Rotate. Today we're going to look at the algebra behind this. So you learned how to pick it out from a picture in geometry. Today we're going to look at how we can pick that out from an equation algebraically. And so before I actually go look at the rules, I want to kind of break it up with these pictures. If I have a point up here, would the corresponding point down there have the same x value, but the y value would be negative?
Yes.
So if I plugged in a negative y, I should get the same value as if I plugged in a positive y. Say x values if I plugged in a positive y. Everyone agree with that?
Yes.
Negative y, negative positive y should be the same x value. On the one with y-axis symmetry, a negative x should give me the same y as a positive x. Everyone agree with that?
Yeah.
And then on the origin symmetry, a negative x and a negative y plugged in would kind of give me the same result as a positive x, positive y. Everyone agree with that?
Yeah.
So, this is how you test for symmetry. This is another note card. I know I'm killing you with note cards. This chapter just has a lot of information. It's easy to forget. We need to have it somewhere you can pull it out handy before the final. So, this needs to make a note card.
Okay. We made an equation for it. We would have to use x squared.
We will talk about that in just a second. Am I out of note cards back there?
We got like one, I think.
Just go ahead. All three of them? I would, but you don't. You can do anything as long as you have it. You could label 3 different note cards, all with symmetry, and I would check that as one note card. So if you want to put it on 3 different ones, that's fine with me. Okay, so let's talk about y-axis symmetry. To test an equation to see if it has y-axis symmetry, you're going to replace the x with a negative x. If you get an equivalent equation as the original, then it has y-axis symmetry. So graphing it. Now, of course, we're not going to throw our calculators out the window and not graph, but there will be some of it that will be easier to do algebraically, because graphing some equations gets tricky, and y is hard to get by itself. You know what I mean by that? So, that's something we'll look at. For x-axis symmetry, we'll replace the y with a negative y. If you get an equivalent result, then you have x-axis symmetry. If you replace x with a negative x and a y with a negative y, and then get an equivalent result as the beginning, then you have origin symmetry. A function that has y-axis symmetry is called an even function, and a function that has origin symmetry is called an odd function. Why do you think think? Someone's really on top of their game today. Why do you think x-axis symmetry doesn't get a full name? So if you have a function that has y-axis symmetry, it's called an even function. If you have a function that has origin symmetry, it's called an odd function. What's a function?
F of Y.
Yeah. And we know that you, and Jacob said, to be a function, you have to pass the vertical line test, right?
Oh, you're
Right? Does any function with x-axis, anything with x-axis symmetry, unfreeze, pass the vertical line test? If it folds over the x-axis, then no. So you see why it doesn't get a full function name? Not a function.
But why is it human?
You'll probably figure that out. That was okay, so the first one, I want to know if it's even, if it has x-axis, y-axis, or origin symmetry. You will get to a place eventually where you can shortcut it. For now, I want to see all three tests on your paper. I want to see the work of all three tests on your paper. For x-axis, y-axis, and origin. Okay, so I'm going to test for x-axis. Y-axis, x-axis, and origin symmetry. So to test for y-axis symmetry, it says to replace the x with a negative x and see if I get the same equation. So I'm going to try it. Doesn't squaring something make it positive? Yeah. So if we agree that that is equivalent to the original, it would, the negative x squared would be a positive x squared. Negative would square out. In fact, to any even power, wouldn't a negative square out? Right? So why do you think we call it an even function?
Okay.
Craziness, right? Anyway, that's okay. So this is the test for y-axis symmetry. It does have y-axis symmetry. Does that make sense? If you get the same equation as you started with, it has y-axis symmetry. So this does have y-axis symmetry. So I take the x in the equation and put it at negative x. Simplify. So square it out. What happens when you square negative? What's negative 3 times negative 3? Right? Anytime you square a negative, doesn't it become positive? So when I square that, this becomes positive. This is the same as the original. So I get y-axis.
How do you know that the y-axis is it?
So if you plug in a negative x, you get the same thing as the original.
What would you do if you like the positive rate?
Yeah, wherever x is, you put a negative x.
Even if it's negative.
Well, then you got a negative. Where x is, you replace it with a negative x. Okay, let's look at x-axis symmetry. What do you do? Replace the y with a negative y. I do want to try to simplify this to see if it's equivalent to the original. Well, the original has a positive y on the left, so you might try dividing everything by negative 1 to get y equals. And if you do, you get y equals negative x squared plus 3. Is that the same same as the original? No. So, no x-axis. Everyone see how that works? Plug in a negative y, if I get the exact same equation back now, it may take some work to get there, but if I get the exact same equation that I started with, then we have x-axis.
Wait, why is it?
I'm still using the same equation from the top. I'm testing it for x-axis symmetry, I'm testing it for y-axis symmetry, I'm testing it for
So you make the y negative b and the x symmetry.
for order. Yes.
Okay, how did you get the 3a?
So this was x-axis symmetry.
Right.
So I just take a y. That's all.
Well, then on the second equation,
Oh, sorry. That's a no, it's not the same as the original.
okay. So how did you put x squared is negative?
So I divided everything by -1. Just trying to see if maybe it's equivalent. And it's not. But you probably could have told that from the beginning, but okay, origin symmetry. I'm going to replace the y with a negative and the x with a negative. You've kind of already done the work on those, so you probably know the answer, but for right now I want to see the work. So I'm going to put a negative in for y and a negative in for x. The negative in the x ends up squaring out. Does everyone agree? And so I get negative y equals x squared minus 3. Kind of the same thing I ended up with over here. Okay. So is that the same as the original equation? So, no origins. So this is how you test algebraically. Now, some of you are saying, hey, if I'm on the final, can I just use the calculator? On that one, absolutely. Isn't it a parabola moved down 3 units? Doesn't it only have y-axis symmetry? So yes. Now, you're probably thinking, well, why then are you making us do this if you can just graph it? Look at the next one. Is it a little bit more complicated to graph? Why is it more complicated to graph? Y squared. If you were to graph it, you have to take a square root. You have to remember to do a plus or minus. You'd actually have to graph 2 pieces. Everyone agree? So it would be much more complicated. So it's not that we're replacing our calculator knowledge, but now we can do a few more that we couldn't do with our calculator, or it would be tough with our calculator. That makes sense? So let's look at this. Now, at first, you're going to just have to work them. Later, you will figure out some tricks. Like on the last one, did you figure out, hey, if all the x's are the even powers, we probably have an even function? So you'll learn some tricks as we work. Okay, so plug in negative x. When I cube, does a negative go away? No, it stays there. So this is just negative x cubed plus 8x. Is that the same as the original? No. So, does not have y-axis symmetry. Do you have a guess at what kind of symmetry it does have? Probably x-axis. Why do you think it has x-axis symmetry?
The y squared.
The y is squared.
how did you get you got negative x plus
happens when I square that negative?
Just y squared.
Is that equivalent to the original?
Sure is.
Absolutely. So, what does that mean?
Yeah, that's X.
That's x-axis. And the last one, origin symmetry. I replace both. If I had one type of the x-axis or y-axis symmetry, but not the other one, is it likely that this one's going to work?
No.
Probably not. We'll do it. Figure that out. So that squares out. This side, I've already done both of those sides, right? And that is not equivalent to the original. So the only type of symmetry I have here is x-axis.
So, you can originally get both of those.
We'll find out, won't we? We'll try. Are they only gonna one at a time? They might have to. A circle. We could make an equation that's a circle, couldn't we? Somebody could. And what kind of symmetry does a circle have? All. X-axis, y-axis, origin. So yes, you could have multiples. You could have all three. An ellipse would also have all three. So there's some shapes that could have all three. That was their question. A circle would have all three types. Does that make sense? And so unless you know how to pick out a circle from an equation, which some of you do because of ACT prep, right? X squared plus y squared equals r squared. So if you knew how to pick that out, you might notice it's a circle and could work with it and figure that out. But if not, you're going to need to check to make sure it's not a shape like a circle that has multiple forms of symmetry.
Wait, rational? Yeah,
Do what?
rational. Like an original. Origin. Let's call it original.
So, rational, like 1 over x? Yes, it has origin. Okay, so let's look at the next one. Now, before I work it, because I do want you on your homework thinking both graphically and algebraically. We are not giving up our graphical skills. I hope you can do the bell ringer. I hope when you come to one like these two, you check it graphically, even if I make you do it algebraically. Can I graph this? In fact, I could even do it by hand without a calculator. Isn't it a parabola moved left 3 from yesterday's notes? Parabola moved left 3. So if I look at a parabola moved left 3, does that have any kind of symmetry? No. So I expect that to be the answer. So I'm going to work it, but I expect that no symmetry is my answer on this one. Does everyone see what I mean by that? So don't forget that we can graph. Some things are hard to graph. It's not impossible. But don't forget to check it. So I'm going to replace x with negative x. You could FOIL if you want to, but are those the exact same equation? No. That one is a parabola moved. That's not the same thing. Everyone agree? You could FOIL it to verify that if you really were unsure. Those are not going to be the same, right? So, does not have y-axis symmetry. Looking at a negative y. Is that the same as the original? You notice I'm showing a little less work as I go because I'm kind of getting the hang of it a little bit. You know, what's the big thing that gets rid of a negative? A square or a fourth power or something like that. So that's where those are going to go away quickly. Negative y equals negative x plus 3 squared. So this is the one that I may be the most unsure of. So I can, if I really want to, I can FOIL that out really quick and kind of see what it looks like. If I do negative x times negative x is x squared. Outer I get negative 3x. Inner I get negative 3x. Last I get plus 9. Divide everything by negative 1. Right there would be enough for me to stop and say these are not equivalent to the original. Because wouldn't the original be a positive x squared? Y equals x squared plus 3x plus 3x plus 9. Right? So right there would be enough for me to say, nope, this is not the same as the original. So that means, in fact, we have no symmetry. We knew we did, right? We knew that was the answer because we graphed. But I also graphed this one. It's y equals, any that are y equals, please check all of those in your calculator. Of course, I'm going to work this algebraically. So for y-axis symmetry, do the cubes get rid of the negatives? Do the cube and multiply by negative x. Does that get rid of a negative? No. So this is how y-axis symmetry.
No.
X-axis symmetry. Is that the same as the original? No. I could divide it by the negative 1 if I wanted to, but then it would make the other side all negative, right? So that is not the same as the original. Does it feel like you're playing that game when you were a kid and you all on all the kids' menus? They're like, which one's it?
There's always like it's negative.
F of negative x, which is what we're doing. A lot of people get confused with function notation and things, so I use lots. But yes, that's what we're doing, because we're putting a negative in for x. So f of negative x. Okay. And origin. Negative n for y, and a negative n for x. So I kind of stole my work from the top two. Everyone see what I mean by kind of stole my work from the top two? Maybe. Divide by negative 1 and see, right? See if maybe it's the same. If I do divide by negative 1, what do I get on the right? Is that the original? Yes. So this does, in fact, have origin symmetry. You notice all the powers on x are odd?
Yeah.
Mm-hmm.
So why is it called an odd function?
Yeah, I already.
Probably just. Okay. Okay. Well, what was the original? What did I get? So I replace the x with negative x and the y with negative y, which got me here. And then I thought, well, I can't really tell because every sign is so I divided everything by negative 1. And it happened to be the
Wait,
original.
so you have to make the x's negative.
And the y's negative.
Yeah.
So
Did you, instead of making like the x negative result, just make it negative 3x?
I did cheat a little. I'd already done the work up here. So I kind of pulled that down. But you can,
Would you get the same answer
Yeah.
if you would have done
Yes.
plus 3 negative?
yes. Because negative plus 3 times negative x is negative 3x. So in your simplification, you want to see if they're equivalent or not, right? So to do that, don't you need to see what would happen if y was positive? Because the original had y positive. So to check to see if they're equivalent, you need to check to see what it would look like. Okay, now, some of you will always hate the algebra behind this. Some of you will love it. And so we need an alternate way in case you get on the final and you're like, I am not doing that algebra, you cannot make me, I would rather fail, right? Some of you have that for some reason. So how can we get the calculator to help us? We need to be able to graph something that's complex. Now, I will tell you, I can make a problem that you cannot graph. So I can't make a problem that you have to use symmetry testing. So be careful. I'm not saying ignore algebra. I'm saying if you get to the point where you just are stuck, how do you use a calculator on something a little complex? Well, how are we going to use a calculator? How are you going to do that? I have to get y by itself. Does everyone agree? When I take a square root, what do I always get? A plus or a minus. How in the world do I type that in my calculator? You do both. You do y1. In y1, you're going to type the square root of 9 plus x. In y2, you're going to type the square root, negative square root of 9 plus x. So get your calculators out and graph those. Do you get this? You type the minus sign instead of the negative sign. You know what I'm talking about?
Where'd you come up with the
So it's a
I had that. So I took the original trying to get y by itself. What kind of symmetry does it have once you see the graph? X-axis symmetry. So this is how you use the calculator if it is a hard one. Again, we could make one that's just impossible, but a lot of times they will be ones you can graph.
Are they supposed to connect to each other?
They do connect. Your calculator will have a hard time with that down there because it struggles with two functions.
Because mine stops before it gets back to it.
Did you ask another question?
It like stops before it gets to the next axis. But it's only
And even though it does, it still has y-axis or x-axis symmetry, so you could probably still get away with it. Okay. Even and odd. I feel like I don't even have to say this because I think I've said it enough throughout the lesson. But if they ask you, determine whether a function is even, odd, or neither. In your brain, you ask, does this have x or y or x-axis symmetry, or sorry, y-axis symmetry or origin symmetry? You won't have to worry about x-axis symmetry because it's not a function. Because x-axis symmetry is what. Right. So determine whether the function is even, odd, or neither. It's really asking, does it have y-axis symmetry, origin symmetry, or neither? So when you read that question, it's the exact same question we answered on the last slide, essentially. Okay? So I don't even have to say it. We can make one up. The only difference in this question and the question on the previous slides is they may write f of x instead of y. How can you fix that? You can write y equals x squared plus 3. And you're going to work this the exact same way you worked the ones on the last slide. Other than that, again, though, you get to skip something. You don't have to check what? When functions, and when it's asking even, odd, or neither, you don't have to check x-axis symmetry. So you only have two things you need to check. Flat y equals x squared plus 3. I heard a lot of you already said you know the answer. Because you see the x squared and the parabola. Oh, that's probably... now be careful if it's x squared plus 3x, that 3x would mess us up, right? So be careful with just seeing an even power and answering the question. But to check, I'm going to put
You always have to check things, please.
it depends on the wording of the problem. If it says check algebraically, then so this one has y-axis symmetry, agreed?
Okay.
Unlike symmetry testing on non-functions, a function cannot be both even and odd. Okay, let me say that again. A non-function can have multiple types of symmetry, like a circle. A function cannot be both even and odd. So once you get 1 on even and odd, y'all were asking me that earlier. Once I get 1, can I stop? On even and odd, yes, you can. Because it's either even, odd, or neither. It can't be both. So on even and odd, you don't have to test both if you find 1. Now, if you don't find 1, you'll have to check both. But even and odd can't happen at the same time. The reason on a non-function that it can't happen is if you have both x and y axis symmetry, you will have origins. But on a function, you can't have x-axis symmetry. So it kind of cuts out that option of being both. Does that make sense? Okay, this is your homework. You have 5 minutes on it. That's 6 minutes on the class. Pull it out. Make sure you can follow the directions, know what you're doing. Or if you have questions from last night's homework, you have enough time to get those answered also.